this is number 1. Okay, let's find the limit. Let's find the limit. S for S prime. Limit of, in this case, S of t plus h minus s of t, that's the original function, over h as h approaches 0. Right? Same formula, but what are we using here? What are we doing here essentially? Well, just adapting the formula for the derivative to position versus time instead of y versus x. Alright? So, that's, well, whenever we see the letter x, we will replace with t plus h squared plus 2 times t plus h, and then minus the original function t squared plus 2t, the whole thing divided by h. Alright, so oops, let me label this. Okay, so this is our f of t plus h minus f of t. Alright? Just so you can follow where are we getting these two from. Now, well, in this case, we would have to expand the binomial squared. Alright, expand the binomial squared, and or FOIL, however you feel more comfortable with. I will go with expanding the binomial because I think it's shorter. So limit as h approaches 0, that's a t squared plus 2th plus h squared minus, let's distribute this -2, minus 2t minus 2h, and distribute the negative over here as well, minus t squared minus 2t. And I know this problem is going to give us a lot of terms. However, a lot of terms should cancel out once we do these expansions. So the t squared, yes, canceled. What else? Anything else? And the 2t. However, it should be plus 2t, right? That's yes, I don't know where I got the negative from. It should be plus and plus, and yes, 2t with 2t. Alright, so let's write down what we were left with. So we will be left with limit h approaches 0, so 2th plus h squared plus 2h over h. And well, thinking of this algebraically, did you see the GCF in the numerator? We can factor out an h 2t plus h plus 2 and over h, and check this out. Cancel the h's, and these h's are the factors in the expression right here that are causing the troublesome 0 over 0. So whenever we have a 0 over 0 on a limit problem, that's always great because we can always find an algebraic way to simplify this. However, the issue is when you have a number over 0, that's not an indeterminate form. In those cases, either we have to look at the graph and evaluate the limits on both sides, so hopefully we can get the same results, or make a table of values, so different approaches. But 0 over 0 is always great. So now that we got rid of this these h's, that's going to leave us with 2t plus h plus 2. So this is plugging for h equals to 0. This is 2t plus 0 plus 2, and this is 2t plus 2. Alright, so that's the final answer to the limit, but and yes, it's a lot of crunching numbers and symbols, but what's this ultimately? So in in physics, well, when applying this to physics, we're given a function, f of x. That function, f of x, relates the position of, in this case, the car over time. When we take the derivative of the function, that derivative represents the velocity of the car for different various times. In this case, if we take a second derivative, which I'm not going to do it using the limit problem, we're going to look at new rules soon. That second derivative will represent the acceleration in this case. But that's going to be a little bit later in the chapter, in the semester. In the meantime, s prime of t, which is 2t plus 2, that's the derivative. This is the velocity function. And in this case, it's the velocity. What kind of velocity? Careful, because notice in this case we're not finding the slope between 2 points. We're not using the secant to find the average velocity. This time we're looking at the instantaneous velocity. So now we can find what's the speed of the car at any particular time, not just the average. So that's the power of the derivative, amongst other things, you know. But the simplest case is the velocity position problem. That's what we start with now. They're asking us to find the car at t equals to 3.
You just plug in.
Exactly. We just plug in, and well, in this case, they're not telling us whether t represents seconds, minutes, hours, years, you know. So just s prime of t, of 3, equals 2 times 3 plus 2. 2 times 3 is 6 plus 2, and that's 8. All right? And that's the velocity. Okay, guys, so finding the derivative, as you can tell, it's a painful process using the limit definition, isn't it? Well, some of you might have taken a calculus class before in high school, or you're taking the class for the second time, not that I want to put you on the spotlight, and you know that there are rules to make this quicker. That's the differentiation rules, and we're going to do that in the next section to avoid this crazy looking process. Nevertheless, on the exam, you will be asked to find the derivative, at least one exercise on finding the derivative using the limit definition. At least one exercise, maybe even two, but the remaining using the differentiation rule. Yes?
Say that we find the limit through differentiation. Can we then just use that to confirm the limit problem? Like
limit through differentiation. I think it's
so like we find the derivative of the function that's right in the exam. Can we then just use that to confirm the limit?
Yeah, oh, of course. For example, you do the whole process here, and if you already know the differentiation rules, you can just do it on the side to verify your work. Exactly, but ultimately, yes, on the instructions it will be specified to use the limit definition, but it's valid to use it just to check your work. Question?
Yeah, and the question is the instantaneous velocity. Don't we have to use 3.01 or near to the 3 in order to get the answer?
3.01?
Like we getting closer to the 3, but not exactly.
Oh yes, of course. I mean, it's a limit. Yes, we're approaching that. Right, that is correct.
So don't we have to find that in this question?
Oh, not anymore, because we're not using the secant anymore. So if we were looking at this problem, the long process of making a table and then seeing a pattern of numbers, yeah, then we would have to look at 3.1, 3.001, 3.0001, and from the other side, 2.9, 2.999, 2.999, etc. But in this case, this construction, this powerful formula for a definition, help us avoid those looking at limits from the side, so we can just go straight to the actual value and not forget about secant lines this time. Yes. Oh, okay, guys. Let me pause it. So instead of using those painful processes to find the derivative, using the limit definition, we are going to use what it's called the differentiation rule. Number one, let's have a look at notation. So notation for the derivative, you might see me using, well, we already used f prime. We can also use y prime, and we have this other notation, dy dx or df dx. That is the derivative of the function y with respect x, the derivative of the function y with respect x, and well, y prime, this prime represents first derivative. Later we're going to look at higher order derivatives, and that's going to be like f double prime, that's going to be the second derivative, but we're going to discuss those later. All right. Well, the derivative of a constant, the derivative of a number, any number, it's just 0. Okay? Really easy. The derivative of 5, 0. The derivative of 7, 0. The derivative of 9, 0. And well, just real quick, let me do the limit definition for this. So f prime of x equals, for example, for f of x equals to 5. So that'll be limit f of x plus h minus f of x over h as h approaches 0. Well, our given function f of x equals to 5 doesn't have any x's to plug in the x plus h, does it? So all we're going to do is 5 minus the original function over h, and 5 minus 5, that's a 0, over h as h approaches 0. Alright? And well, this is 0. So that's why the derivative of a number is just 0. Well, I'm not going to justify every single formula, so I will just give you these formulas. Alright? The derivative of power functions, like the derivative of x, is 1. Well, where is that coming from anyway? So if you relate this to like y equals 1x plus 1, that's to relate this to the mx plus b, to the mx plus b form. But what's the derivative? Isn't it the derivative the slope? And for this function y equals x plus 1, what's the value of the slope? Isn't it 1? Well, so the derivative of x is just 1. Now, what about the derivative of x squared or f of x equals x cubed? Well, we already did the derivative of x squared using the limit definition. Okay, let's do the derivative of x cubed using the limit definition just briefly. Alright, so f prime of x equals limit x approaches, oh, not x, actually h approaches 0. That's the quantity x plus h cubed minus x cubed over h. Well, in this case we need to expand the binomial cube. Well, how to expand binomials beyond the square? Well, you need to use the binomial theorem that you learned in pre-calculus. If you don't remember this, well, I'm just going to give you the answer. I won't expect you to know this binomial. So that's going to be x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed. That's over h. And let's see how x cubed and x cubed, negative x cubed cancel each other. And this is going to leave us with, we can factor h's here. Limit h times 3x squared plus 3xh plus h squared over h, and that's going to leave us with limit 3x squared plus 3xh plus h squared as h approaches 0. Now, when h approaches 0, This term will go to 0. This term will also go to 0.
Wait, why does the x cost up 2? Shouldn't it be differentiation?
Yeah, but because it's times 0,
Oh, equals by 0.
yeah, they're multiplying, so that zeroes out, and we're going to be left with 3x squared. All right? I mean, even for the cubic, it's not that bad. However, what if you are being asked to find for f of x equals x to 100, right? Find the derivative of x to the 100. Okay, f prime of x equals limit of x plus h to the 100 minus x to the 100 over h. So in the previous exercise for the cubic, we used the binomial theorem for the binomial cube. Or you can FOIL it this, an alternative is to do x plus h times x plus h times x plus h. Alright? That's an alternative way to do this. And it's alright, just FOIL as many times. However, this guy right here, I'm worried about this one. Do you feel like doing x plus h times x plus h times x plus h dot 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 x plus h? Do you feel like doing that 100 times?
Could you actually work it out on the board for us?
I can do that, but this is broken. I cannot lift it. Otherwise, my pleasure. They're gonna fix it next month, so they say. Well, unfortunately, it's not practical to do this foiling 100 times. It would take, I don't know, maybe the whole weekend. But for this, we just use the general power rule. The general power rule. So that is, subtract 1, multiply by the exponent, and subtract that by the new exponent. Okay, so for example, y equals to x cubed and y equals x to the 100. We're no longer going to need the limit definition. So what we do here is multiply by the exponent y prime, that's 3, x to the 3 minus 1, which is 2. You see how we got the derivative in seconds? Instead of going through the limit definition, which took, what, 5 minutes maybe? Alright? What about x to the 100? Y prime equals 100 times x to the 99. That's it. Alright? And no need to FOIL x plus h 100 times and hurt yourself. Alright? Let's do a few examples on finding the derivative using the general power rule. Well, y prime 8 x to the 7, that is multiplied by the exponent, that by the old exponent, and subtract 1 to the exponent. That's the derivative, and no need to do anything else on this one.
Why are you adding 7?
Huh?
Why are you adding 7?
Adding?
As an exponent. Why did you put 7 as
Yes, that's the formula n minus 1, so we subtract one integer to the exponent.
Oh, and
Yep. This one, be careful. So although this general power rule looks really easy, and in fact it is, be careful. Because we cannot take the derivative. This is not going to be 6x to the 5th. No, that's not how it works. First of all, we need to rewrite this with x in the numerator and negative exponents, x to the negative 6. From here, we're ready to take the derivative. F prime of x equals negative 6, have the exponent to jump in the front, x to the negative 6 minus 1. What's negative 6 minus 1? Negative 7. And what we're essentially done with the calculus, the rest of the problem is algebra. You might want to just write this negative exponent as positive exponent. Negative 6 over x to the 7. That's final answer. Letter C. Letter C has radicals, but well, that doesn't look like a power function, and in fact, we're gonna make this look like a power function. Yes?
We could do it x raised to power 1 by 3. X raised to power 1 by 3.
Yes, by decrease by 1. So negative 6 minus 1, negative 7. So in this case we have negatives. So now, for the radical, yes, this general power rule is going to work. However, we need to write this as x to the rational exponent. What would be the exponent here? 1 over 3, 1/3. Okay, y prime, that's have the power to jump in the front, 1/3, x to the 1/3 minus 1. Now, here is where we're going to need to subtract fractions. What is 1/3 minus 1? Negative 2/3. In other words, 1/3 minus 3/3. Yes, indeed. Y equals 1/3 x to the negative 2/3. But that's not the final answer. We're just done with the calculus part of the problem. The remaining part is using properties of exponents, laws of exponents. This will be number 1, 1 over 3 x to the 2/3, and going back to radical, that's 1 over 3 cube root of x squared. Recall that the denominator of a rational exponent tells us what the index of the radical is. Alright? Denominator of the rational exponent, that's the index of the radical. Alright? The derivative for letter G, for letter D rather, g of x e to the 8th power. What's the derivative of that function? Well, we haven't done the derivative of an exponential function yet, but well, ultimately, what's e to the 8th? What's that? Isn't that just a number? Isn't that just a constant? What's the derivative of a constant? 0. F of x equals x to the pi. Well, we have worked with integer powers and rational powers. Pi is an irrational number. All we have to do is f prime of x equals, have the pi to jump in the front, x to the pi minus 1. That's it. Leave the answer in terms of pi. Don't do 3.14 minus 1 equals 2.14. No, just leave it like this. That's fine. Oh, one more. One more. Y equals 1 over the cube root of x squared. Number 1, we cannot use the general power rule while two things. Number 1, we have a radical form, and also we have the expression in the denominator. So number 1, let's rewrite this as x to the 2/3 and send this to the numerator with negative exponent. Alright? That's basic properties of radicals. Now we're ready to take the derivative because we have the form x to the n. So we're going to do the exponent to jump in the front, y prime, negative 2/3. X to the, what is negative 2/3 minus 1? Careful.
Negative is 5.
Negative 5/3. Okay, essentially, this one is the same as saying 3/3. So negative 2 minus 3, yes, that's indeed x to the negative 5/3. But that's not the answer. We're just done with the calculus. Let's write it in radical form. Negative exponent, send it to the denominator with positive exponent. And well, what do we have in this case? Rational exponent. The denominator of the rational exponent again is the index of the radical, and in this case it's a cube root. That is 1 over the cube root of x to the 5th. Final answer.